So my workaround to get the screen black is to have a black picture that I put on full screen. The screen is on. Okay, okay, welcome back to the lecture. Now also welcome to the online audience. We managed finally to record this. So I gave as example 3 all mathematical statements, true or not, just well formed. It's kind of easy that we can encode in a 0-1 sequence. I think everyone believes this, no? And then I say that we cannot just list all of them, and to make this more rigorous, let's define the term decidable. And something is decidable if and only if there exists an algorithm A, so some language L is decidable, so that for all W element L or all W element 0-1 star, AW returns the correct answer in finite time. And the finite time is important because you can go through all mathematical statements and you can list all possible proofs and check if this proof proves the mathematical statement you have. And if the statement is true, A will return at some point this statement as true, and this is a proof. However, it cannot do so in finite time. The time can go arbitrarily long because there may just not be a correct proof for it. And then Gödel and found this incompleteness theorem, which said that example 3 is undecidable. And if you take away the technical fluff, it's a very easy argument. It's diagonalization. It's similar to, so we use diagonalization also in to list all natural numbers, showing that there's a bijection between natural numbers and natural numbers, rational numbers and natural numbers. Okay, so far so good. So now we know what languages are, what and even know that we can, even if we define them, we may not know who's in there or not, and that's a problem, and how they relate to algorithmic problems. And it's great that we know some languages are undecidable, but remember that languages are just mathematical objects, right? So we can represent each language by a little dot. And then we have those dots, which are undecidable. And then we have those dots, and we may not know for each language whether that's decidable or not. And then there are those dots, which are easy. Right, so we have a fast algorithm, and we do know that we have that we have one. And then we have some other dots, and we don't really know what's going on with them, right? So they are like, yeah, we don't know. We don't know. They may be decidable, right? But So they are maybe not those, but we're not really sure they're easy. But one thing we can do is we can maybe say that they're all equally difficult. And this all equally difficult is a little bit difficult or to define. I mean, maybe I just say this for as a notation. But those who follow the algorithmic class, algorithmic, they will learn this in more detail. Covers this in detail, and often to really understand that it takes several lectures. So let me skip it here. But so the question is, I would like for a language to know, can I solve it in an easy way, or is it maybe very tough, right? And there may be different levels of toughness, but maybe something I can figure out instead. I cannot figure out how difficult is a language, but maybe I can figure out that all of them are equally difficult, all those languages. And then I have another set of languages. And maybe they're also all equally difficult. And then if we have like 20 of them, we're like, okay, it's interesting, they're equally difficult. But once we have like 10,000 of them, and over like decades, no one managed to solve them efficiently, this gives us a good reason to believe that it would be a tough to make progress on this. Doesn't mean it's impossible, but it means for the state of the art, it would make huge progress. And this gives us to complexity classes. And complexity classes are sets, or let's say families of languages. So by the way, the word family and set means the same thing. We just say, in order to avoid sets of sets, we say families of sets. Families of languages that are equally difficult. Or actually, where typically it's where we have, they're all small or equal to difficult to some specific problem. Like a reference problem. So maybe there's one problem where we say, if you're less or equal to difficult to this one, we're good. And the same here. Maybe we just single one out. Is think about these as representatives maybe of those equivalent classes. And now for this, I would like to give an example as well. And this example is called NP. It stands for non-deterministic polynomial time. And here SAT, which is an abbreviation for satisfiability, has as input binary formulas. So something of the form of x1 or x2 implies x3 and x1. And then the question is, does there exist these x1 0, 1 vectors basically to make this, so this is an assignment. Let's call this formula phi to make Pi true. And who has seen binary formulas before? Computer scientists should raise their hands. Mathematicians, no? Okay. It's like a logical formula. Did you have logic? No? Elementary logic? Is not taught at. Okay. Yes. Yeah, that's maybe a better term. And I should capitalize Boolean because I can. Bool is this. I think it was a guy. Okay. It's maybe not so important here that you familiarize yourself so much with this specific problem set, but just that you think about, okay, so all problems that are small or equal to the set problem, they are all contained in NP. So actually, if we think about NP, then we say, okay, we're actually not saying equally difficult, but we say everyone, um, maybe also who's easier than that. That's also okay. Or whatever we have easier for. And then we have the term NP hard. So language is NP hard if L is more difficult than SAT, and L is in NP if L is easier than SAT. And L is NP complete if L is both. So everyone is easier is in NP. Everyone who's more difficult is NP hard. And if you're in NP and NP hard, you're NP complete. So these are then the most difficult problems. Those are maybe easier, and those are maybe even harder. They may not be in NP. And then one of the exam questions that I put is, which is one of the biggest open problems in computer science? Whether P is NP, yeah. So open problem. We have again our landscape. This is NP. And somewhere here are all these easy problems. I like easy. But actually, is there a problem that's actually more difficult? Are those the same? Or is there something in between that's in NP and harder than these problems? The green is P, yes. Thank you. And just P stands for polynomial time solvable. So NP is a complexity class. It's a family of problems. And SAT is one algorithmic problem. So think of this is SAT, this is an NP. Yes. It stands for satisfiability. That's the abbreviation. Um, and as input, you get a binary formula. So you know what a binary or Boolean variable is? There's a 0, 1 variable. And then you can use logical connectors like and, or, not, implication as you like. You can actually, there are lots of different definitions. Typically in computer science, we use and, or, not. But there is this not or, and if you have not or, then that's sufficient. You only need one connector, and then you need to have well-formed parentheses. And then you want to know, can I find these 0, 1 things to make that thing true? Like 0, 1 variables for each variable, like an assignment, sorry. Yes. And the thing is, we know how to do it in exponential time, but just go through all of them. But we do not know if we can go significantly faster. Yes, and let's say the research of the last 20 years, also what Jesper Nidelov is doing heavily is trying to assume that we cannot go faster than exponential time. And then with this, we can have very precise answers on what is the best possible algorithm for lots of problems. So for some problems, even in P, so that we can solve polynomial time, we have now results that state, under certain assumptions, that we have n squared time algorithms and we cannot go faster than n squared. And this is all based on a hypothesis on how fast we can solve that. So this is called fine-grained complexity and a new line of research, yes? No. There are lots of NP-complete problems that are not set. They're just equally difficult. But what does difficult mean, I cannot define within, you know. But this is not always trivial or easy to see. Okay. I know I go pretty fast, but just to have like a starting point to tell you about my research, I need this a little bit as a backup. Because now we are ready to go into the complexity class that I do research on. And so this is called Existential Theory of the Reals, and they're like this term comes up more often. So we have this, let's say, language ETR, and that stands for Existential Theory of the Reals. And this asks, does there exist x1 to xn element R such that we have a polynomial P that evaluates to 0. So here, this is a simplified definition. I don't want to go into the full scope of ETR. But this specific problem is also called feasibility. So we have this polynomial P. So those who took algebra, they will know this is a notation for the polynomial ring with integer coefficients, but this is just a different notation for P is a polynomial with integer coefficients. And so you don't need to remember this. If your computer scientists just ignore this part, if you have not known what it is, but P of x comma y could be, for instance, x squared plus 5xy minus 10y to the 5. This is an example. So if you, so who had, who knows this notation? Okay, so some, I assume the computer scientists did not see that notation before. No. It's not so important. It's just a fancy way um, of writing that it's a polynomial in these variables, in n variables, but for instance, you could have also just two variables. And then it says that you can't have like pi x squared, right? You have just 2 or 5. Just these things here are called coefficients. Coefficients. But polynomials you've seen, right? Also the computer scientist. This is something you should have seen in school, I suppose. Typically only with one variable, and then you have this to solve. Usually in school, at least in Germany, we have this. You have this formula. If you have a quadratic equation, how to solve it, and so on and so forth. And so what I found curious about these polynomials, that if you have only one variable, there are formulas to describe a solution if you have degree 3. There's also, if you have just one variable, to describe solutions for polynomials with degree 4. And for degree 5, it's impossible, and this comes out of Galois theory. This, maybe Gabriella knows more than me about it. Okay, so, and then we get a complexity class, which is called ER, which is pronounced as in different ways. So pronounced as ER or exist R or ETR. Different people have different notations for that, or ways to pronounce it. I typically just say ER, but I'm just one person. The person who introduced this notation says exists R. He's also German by coincidence, but he is at DePaul University in the US. Okay, so that's a complexity class that corresponds to it. And this is my research topic, to work on this complexity class. And that may sound a little bit boring, but let me go to the part where it's getting exciting. But I want to have a few more things that I need to tell you. So it is known that SAT is less difficult than ETR. And if I would give you a more precise definition, maybe we can, Gabriella, maybe we can do this as part of the tutorial. If that would be maybe a good tutorial question, and then you need to learn some tricks, but then Gabriella can help you. And so this implies that NP is a subset of of ER. So there's these problems where we don't know how to solve them, and I study problems that we know even less how to solve them. How interesting is that, right? So that's maybe I'm playing here devil's advocate, but that's maybe why people haven't really considered this class so much. They're like, oh, it's NP hard, it's difficult. And then I don't care exactly how difficult it is. I know it's difficult. But there are some subtleties that may be worth exploring. Namely, they're just different levels of difficulty. And let me check the time. We still have 10 minutes. Very good. And for SAT, we have simple exponential time algorithms. So if I tell you I have a SAT formula with 20 variables, and I give you a computer and I give you 4 hours to program, you're gonna tell me whether the SAT formula is satisfiable or not. Right? You just hack it into your computer or you maybe switch on Chat GPT that gives you some code to test if this formula is correct or not. You could just go through all the 2 to the 20 many possibilities. And if you're a little bit clever, then maybe you break it down to 2 to the 10. And then in a milliseconds, right, a computer can solve this. Now, if you have millions of variables, they're so-called set solvers, which branch in a stupid way, but then they do backtracking in a more sophisticated way. And they can also solve set instances of millions of variables in a reasonable amount of time, maybe an hour or so. And at some point, they come to the threshold if they say, okay, maybe we can do it for 500,000, but not for 2 million, right? But large instances can be solved. And then there are even ILP solvers, integer linear programming solvers that maybe Han and Marian and operations research people use, and they can solve even bigger problems in a reasonable, fast way. And they're based on branch and bound and simplex algorithms and other interesting things. Did you have classes on this or okay? So you know, if you have a question about this, you can ask Gabriella. And they're also super fast and they give optimal solutions and they give proof of having the optimal solution. Okay. So when we say we do not know if P equals NP, we can still solve NP problems pretty fast. And now we come to ER complete problems. ETR is basically there is no algorithm without knowledge of algebra. There are some easy algorithms and they're also typically very fast, but it's not like I can just try out all solutions, right? I need to know something more about algebra. There is something like a 10-page algorithm that I think if I give you more instructions and a week of time, you would be capable of implementing. But it's not an easy algorithm, and it's also not the best one we have. And then the best algorithms, I don't understand, right? So you need to take algebraic geometry and then specifically about the reals, and few people are there that understand them. So one thing is we don't really have algorithms without knowledge of algebra. But even worse is in practice, even if you have these algorithms at your disposal, we can solve only very small instances. And here I would say optimally. Because there is a big class of problems that we can solve optimally and that are huge. Yeah, so maybe for ETR, I can also say discretization unlikely. Do you know what I mean with discretization? So you have here continuous variables, right? And you cannot try out all of them. So it would be nice if you can just say, well, we don't try the infinite ones, but maybe we just take step size 0.1, try all of those, and hope that this gives us a good enough answer. So that would be discretization. And depending on the algorithmic problem that there's at hand, there are different ways of discretizing the solution space. But this ER completeness means exactly that this is very unlikely. Because if you could, then you could take your discretization and translate it to all the other problems. Okay. And now many of you have seen many NP-complete problems. So for instance, we studied coloring. So that's an NP-complete problem. And you also have seen ER-complete problems. You have not been aware of they being ER-complete. So let me give you some examples. So example packing. In packing, we have as an input a container. Right? So think about box. But here we just think of this as in the plane and items. Maybe a triangle. Maybe what else could we have? Pentagon. Yeah, also of the plane. And I could say polygonal. And then the question is, so can I use rotation plus translation? Can items fit into the container? Okay. Okay, I'm gonna go a little bit over time and then we do the break. Is this algorithmic problem clear? Martin, clear? Very good, because no one has. Do you know why no one has? Exactly. So there are a zillion of papers on packing, but they never allow continuous rotation. And if they allow continuous rotation, then they are I think there are one or two of them, and then they usually say we can pack 5 objects optimally. Yeah. Um, so yeah, so actually packing is a problem that studies in lots of different domains. So in mathematics, in computer science, operations research, but also in industry, it's a really relevant problem, and that also appears in daily life, right? I guess everyone came today and they put some bag and they put items into it. It's a packing problem. Okay, my bag is more flexible. It makes it a little bit easier. But those are packing problems. Even three-dimensional packing problems that are even more difficult. Um, yeah, so this problem is ER complete. And somehow to show this, we had 2 papers. One of them I wrote with Rainier Schmiermann, who did his master's thesis, which, yeah, I don't know. I think for some others it would be almost, well, I wouldn't say this, but he's very, very strong. I think it would be hard to have written this paper with someone else. Who have heard of Rainier Schmiermann? You know Rainier, okay. So we wrote, let's say, 50% of this paper is a collaboration with Rainier. Um, and and just to illustrate you how hard this is, we have these 11 unit squares. So 11. So this thing is sometimes people don't understand this. Can you lend me one finger? Okay, can you hold it up? 11. Right, it's a very small number. It's really not that hard. And we want to fit them into a square container. We don't know how to do it optimally. And it's a first non-trivial instance. There are some very complicated packings. And if you read XKCD comics, then you know you can optimize them with a press, hydraulic press. But okay, yeah, but we don't know how to do this. And one of the explanations is, well, this is an ER complete problems, and we cannot solve them optimally. Yeah, and yes, see, that's the point. Okay, let's meet again at 10:00. Okay, welcome back to class. Somehow I'm strangling myself here. Didn't do this very cleverly. Um, so we know now one example of a problem, of a natural problem that is ER complete. And we also saw, okay, that even the simplest instance that we can think of, we can often not solve optimally. This is not true for all ETR complete problems, but it's very typical. Um, uh, and I could give more examples, but it always takes a little bit time to explain it. But let me maybe write some lessons that we can have from ETR completeness. So discretization, uh, unlikely, or at least very hard. Uh, um, even exponential time algorithms are hard to find. So there are a lot of open problems where some scientist says, "How about this problem? We don't even know if it's decidable, um, because these problems were in ER." Uh, so even exponential time algorithms are kind of hard to come by, and they always rely on these algebraic algorithms. Um, and if you want to do something about them anyway, you can, but then use additional assumptions. And so, for instance, I showed using smoothed analysis that packing can be discretized. For the art gallery problem, we developed specific assumption which also showed they can be discretized, and there we could even solve large or medium-sized instances, maybe 1,000 vertices, optimally, and the algorithm was provably optimal using those additional assumptions. Um, and that was the first algorithm ever to do that. Another way to go about this is to use heuristics. Um, so heuristics often are used in a derogative term, in a derogative way when I speak. Algorithmic people talk about it. They're like, oh, these are just using heuristics. But actually, it just means we don't know how to prove something about it. But actually, they should be really interesting because they're often very fast. So we should try to understand why they're so fast. And there are approaches in the, let's say, in the more advanced, in the more recent algorithmic literature on how to do this. So there's this course beyond worst case analysis in the master math that I would recommend everyone. If you want to understand more about why heuristics work, they give an explanation why simplex algorithm works. They also, and 2opt, maybe the people who took optimization, this operations research course with Han, they have heard about 2opt. There are explanations why those work. But heuristic just means no proof, like no mathematical proof of correctness. But there is another lesson, namely try methods that worked for other ER complete problems. And the most common one is gradient descent. So if you have a problem and someone tells you, oh, we figured out it's ER complete, and you're working in some company and you're meant to solve this, don't try stat solvers, don't try ILP solvers, try gradient descent. Right, that's the message you have. And if you have this colleague who said, yeah, I worked already for 3 months on trying to make my ILP solver work, then you're like, you're complete. Okay, don't be snobby, but yeah, you know, sometimes people don't listen, and then later, yeah, they have to pay. Okay, so now we know what is ETR. We know the definition. We know the motivation to study it, but it would be useless if there are no ETR complete problems. So let me give you some examples. So namely the question, is ER relevant? If packing is the only problem that's ER complete, maybe we don't really care. It's one problem. Okay, we know it's difficult. But there are a lot of problems that are complete. So packing we already have. Then the art gallery problem. There are lots of graph drawing problems. So what we had so far, we had like a glimpse of graph drawing, right? So we learned there are graphs that are planar, and we learned a little bit about this. But there are a lot of graph drawing problems where we try to place vertices and try to make it look nice to some rigorous definition of nice, and those are typically complete. There are some problems also with polytopes. Let me write realization. So this is maybe one of the most famous problems. So you know that if we have a planar graph, we can draw it on the sphere, right? And we can decide in linear time. So now imagine I give you and a planar graph has vertices, edges, and faces. Now imagine I give you the 4-dimensional version of this. So I give you vertices, edges, faces, and 2-dimension, like 3-dimensional faces. And I want to realize it in 4 dimension as a 4-dimensional polytope. Then it's also ER complete. So I cannot formalize it here without spending a lot of time. There are matrix decomposition problems. Matrix decomposition problems come up in various areas. Typically, for instance, statistics. Because maybe these matrix decompositions, they tell you something about data distributions. So, and one problem that I find very interesting is training of neural networks. So who knows what a neural network is or has seen it at least? Okay. Some people not raising their hands. What? You've never seen neural network? Not a definition, but you heard of it, no? Okay. So at least everyone has heard of it. And yeah, we could also show that this is also ER complete. And what happens is it answers a fundamental question, namely, why do we use gradient descent to train neural networks? And people say, yeah, it works. Yeah, but why doesn't ILP solvers work? Why does set solvers not work? Well, we didn't know how to do it, but people tried how to do it and they failed. Why did they fail? Maybe someone gonna succeed in it. But they cannot, at least not without additional assumptions, because this problem is ER complete. But here, training of neural networks, this is also one example where we can train giant instances, right? With billions of variables to very, very high precision. And this shows you that the rule that I had with these 11 unit squares, where we don't know the optimal solution, is in stark contrast to neural networks where we can solve giant instances. So what this tells you is that mathematical results are they're not translating always one-to-one to the real world. Yes? Is it, I- you're not, yeah, so what you want to do is to define it rigorously, you first need to define what a neural network is, and then you want to have a yes/no instance. So you give a threshold t, and you have an error measure, and then you have a set of data, and that's why it's about training. And then you look at your training error, and you want to know whether it's lower than the threshold. Sorry? Yeah, so there is this discussion. So we have uh, uh, different notions of what optimal means. So typically, if we are in complexity classes, we have decision problems. So the answer is yes or no. And then in optimization, we have maybe a cost function, and we want to optimize this cost function. But these two problems are closely related. Namely, what I can do is if I have an algorithm that can decide yes or no, I can do binary search on my target. Right? I have a target and I say, I want to have an error which is smaller than 100. If I'm capable of doing this, I can ask, do I have a target that is smaller than 50? If the answer is no, I can say, is there something that's smaller than 75? And then the answer is yes, and then I can binary search my way up until I get arbitrarily close to the optimum. But maybe what I can do as well, I can have my target t. I say I want to have an error which is lower than 100, and I would like to know that it's maybe not possible to achieve that. Um, and and in that case, I would want to have a no answer. And gradient descent never gives you no answers. It only gives you yes answers. But sometimes you just wait and nothing happens, and you conclude, well, it seems not to work. But maybe it did work, right? Maybe you just set your parameters incorrectly and so on. Okay, so here I've given some example problems. Admittedly, if we compare this to NP completeness, there are probably 10,000 of problems that are NP complete. We now try to write a compendium, and there may be on the order of between 50 and 100 problems that are ER complete. So really a huge magnitude smaller. But at least what I would say is some of these problems are really important. NP complete are also really important, but I think some ER complete problems are as well. And in the remaining half an hour, so I have a little bit more time than I expected, I would like to show that, like, as I said, this paper here has something in the order of magnitude of, yeah, the first iteration had 100 pages, and then the follow-up paper with Rainier was only 30 pages, and it just fixed some small step. And then this paper also became shorter, but I would like to maybe give some ideas of why packing is ER complete. And I want to give here some proof ideas. And there are 4 ideas. And number one is we, instead of reducing from this problem ETR that I showed you at the like half an hour ago, we reduce or we need to show that packing is more difficult, right? Than this problem ETR, but we have an intermediary. So we have this show that ETR inf is ER complete. And the idea is we have ETR smaller or equal in difficulty to ETR inf, which is smaller or equal to pack. So instead of reducing immediately from ETR to pack, we show that there is a problem in between, which we call ETR inf. And that makes our life easier. And I will define it, but first I want to give an overview. So we need to be able to encode variables into items. So here we have geometry and no variables, and here we have real variables that we have to somehow see how they correspond to geometry. The step is like easy, but I think if you have never seen this before, then I think that's something important to understand. And then the third idea was maybe the most technical part, and this is the placement problem, maybe. Right? You want to encode a variable, and it should mean something, and you say, well, it should be here, it should be there. And then your interpret is in a certain way, but you know you have only this container and these items, and they could lie anywhere you want. And we solve this placement problem, which is making sure that maybe this little rectangle is in the left corner and this other rectangle is in the right corner, and so on. And you will see this what it means. And the fourth thing, so we have variables, but we will also have things that these variables need to do, and these are called constraints. And the fourth thing is to encode constraints. Okay, so let's start with number one. What is this ETR inf? We asked, does there exist x1 to xn, let's say in the range of -1 to 1, such that constraints C1 and Cm are satisfied. So all of them need to be satisfied. And so how does a constraint look like? You remember the definition of a packing, right? I can erase this. And here I'm lying a little bit. The I constraint is either x times y equals 1 or x plus y equals z. maybe let me give an example. So there exists x1, x2, x3 such that x1 plus x2 equals x3 and x2 times x3 equals 1. And the solution would be right, that would work. And here the idea is we started from this polynomial, and we need to show, right? So we started from this polynomial, and we need to show that we can encode it into this ETR-inf. So we have to show that ETR-inf is more difficult, and all that we do is basically simplify formulas scale solutions, and then replace multiplication by inversion. And in the tutorial, this is covered here, how to do this. I think I put this on the tutorial sheet. I assume this is a little bit abstract for you, but I hope you get a glimpse of what is done here. And maybe since we are good in time, I want to maybe say something. What we did with Rainier is, let's say, Rainier, we replaced this x times y equals 1 by f of x comma y equals 0. So and we just said instead of this x times y equals 1, which is a type of constraint, we just say, well, we abstract it. We just say it could be some function f. And we basically said f can be anything curved. So if we have a coordinate system, then it needs to go through 0, but it needs to be curved at 0. And we don't really care what it is. Which is a very powerful tool, which we only used in packing. Otherwise, inversion is usually powerful enough and easy enough. Okay, step 2. So we have this variable x, and somehow we managed to plug it into this range from -1 to 1. And then for each x, we get an item. And somehow we built a tunnel. And I can't really explain you how to build a tunnel, but one easy way to do it, to build this tunnel, is just use a container, right? So maybe this item gets green, and I place this item here, and somehow I'm sure it must be here. This is a problem I'm gonna address later, but then I can move this. Maybe I have a range to move it. Right? Okay, somehow I magically say, this is my container, this is my item. I say this item must be here, and it's stuck in this tunnel, and it can move a little bit to the left and to the right. And now the position corresponds to the value. Let me just draw this like I could position the item here. Then that would be -1. And maybe I can position the item more to the right, maybe here. And that would be +1. And any position in between would be a value in between. This idea is understandable? Okay, now we come to the most technical part of it, which, okay, maybe since we have time, I can give a little bit more of details. So we have this item, and we have this tunnel, and we said, well, this item moves here, and we interpret its position. But there is no reason this item needs to go here. It could be somewhere else in this big container. And the idea here is very simple. We build several tunnels. And this tunnel has height 1. And then maybe this tunnel has height 0.5. And then the next tunnel, or maybe I should draw them actually smaller. And there's another tunnel. Okay, now I'm challenged. And that tunnel has height 1/3. Now item 1 fits here. Maybe item 1. And then item 2 has no place here. Item 2 needs to go here because this is blocked. So maybe there are more copies here of item 1. Right, and item 1 cannot go anywhere else, so it blocks this tunnel, and then item 2 goes there. And the same goes with item 3. Item 3 now is much smaller, but everything above is blocked. So maybe I can introduce this term slack. Slack is the area of the container minus the area of the items. And this will be small. So the difference between the area that the container has and the area that the item has is very small. So they have a little bit of wiggle room, but not actually enough wiggle room that item 3 suddenly can go somewhere else. So everyone has their own location. And now maybe the astounding thing is that to build these tunnels, we will not rely on the container. but our container, so we managed to get the container, in our case, is a square. And to achieve this, is use this idea, this fingerprinting idea, and then add steroids. So this is very hard to imagine, but these ranges that we're having, here's these -1, 1 ranges, we can make them arbitrarily small. And then everyone has arbitrarily small wiggle room. And our pieces will also be convex. And then you have these little gaps, and there's only one piece that fits into this gap, and it creates another gap. And then into this gap, only one piece fits. And in this way, we build all the tunnels. And there's still a little bit of slack, but the slack is so small that it doesn't matter. And then we can still wiggle. We have still enough slack over so that everyone can wiggle. But this is really, yeah, very technical. The reviewer said they're not capable of verifying it, but they think it's true. Yes? Add steroids. You know what steroids are? If you want to have big muscles. It's a metaphor which just says that you use this idea excessively. So we use it again and again and again, and with extremely small fingerprinting that we, carries on with extremely small ranges. And idea 4. So now there are more details, like we have to wire these values to the right location and so on, but that's easy. And I want to skip. So we have then now we go to the constraints. And to build the constraints, there are lots of different ways to do it. But this is where Rainier came in. So one very easy way to add steroids, not steroids, but to add constraints is different colors, blue maybe. So I think we call it a teeter-totter. So we somehow used as a scheme for our paper all these playground things that you can find there. And what you can imagine is, maybe I need some tools here. So you have maybe this item and it's lying on a peak, and then you see that? And what you can see is that this relation between those two variables here will be nonlinear. So if you push this up by some unit, it's not that this unit moves down by the same amount. That looks a little bit counterintuitive, but it doesn't. And what we needed is we wanted to have this inversion. And maybe the first thing to notice is here that this gives us an equality, but an inequality, because I could just move both of them down. And we used convex, but curved pieces to get really this inversion. But this constraint that we have here, right? It's wild. Like we can't even express it. We don't know exactly what it is. But we could show with Rainier that it is something that is curved. And that was the end of the story. So we worked really hard to get the right constraint, but then we at some point we gave up, and then we said, okay, we can save the paper, and it was still very highly regarded paper. But then with Rainier we just said, what about we can just show that any type of constraint is enough to show ER completeness, and that's what half of the master thesis of Rainier was. So this is really impressive. He wrote as half of the master thesis a very strong paper. But this is a constraint idea. Is this constraint clear? Maybe I should add some text. So I've received this feedback that in other mathematics lectures, you don't see pictures and you're confused by pictures. So I add more text. So maybe this gets rotated. But this should just give you an idea how these constraints work. So I also made exam questions out about the content that I presented here. But please check the exam question and write me an email if you find the questions a little bit too vague. Okay, so we have some time left, and now I need to improvise a little bit. But it's maybe also a little bit exciting. So what are open problems? And somehow, yeah, it's a little bit funny because I wrote this grant proposal, which I said I want to do more research on this. I love lots of open problems, but I think some of the most important open problems are a little bit established for me. But there may be different directions one could go to. So maybe one very exciting direction is the following. So we have convex programming. Who heard of convex programming? Okay, so everyone knows what a convex set is, right? And now what I can say is in convex programming, I have this convex set. This is not convex. And maybe in higher dimensions. And I have this objective. This is my set. And this is maybe my objective. And I want to either maximize it or minimize it, doesn't really matter. And then, this is my optimal solution. And now there is a conundrum in convex programming, which is they say, oh, we can solve it optimally using the ellipsoid method. So there are people working at CWI who all their research is about finding better algorithms for convex programming. But we do not know whether this problem is polynomial time solvable. So that's an open question. Is this problem polynomial time solvable? And the answer is, in case that the solution has a short description, the answer is yes. There's algorithms that basically approach this thing, and they approach it faster and faster. And if we know that the solution has only polynomial length, then we can do it. Or what we can do is we just, since we approach it, we just stop and we're like, we're epsilon close to it, we're fine. But if you actually want to find the optimal solution, this is unknown. And so this would go a little bit too far to explain, but assuming NP not equal to ER, this is my belief that this implies convex programming not polytime. And I would go a little bit too far, but to explain why. But maybe the idea here is that this is a simple problem. It's clearly not ER complete, but it is definitely continuous. And maybe we can bridge the gap between NP and ER using convex programming. And if we could do this, then we had this implication. But this would also imply that different models of working with different models of what means to compute would be different. But again, that would be going too far to explain. But there would be maybe one a really big open problem. But to maybe go to a little bit easier ones. So there would be, for instance, problems in graph drawing. So we have in graph drawing all types of graph classes. Okay, let me maybe not go so much into detail, but there's graph drawing, matrix decomposition, and many more. And it would be nice to establish their ER complete. And the idea here is to go from 50 to 100 ER complete problems. To maybe 1,000. Because so who has of you have heard before this class of NP? Okay. Who of you have heard of this before this class of ER? No one, right? But lots of problems that are relevant are ER complete. Just the issue is it's much harder to show. And we don't have the right techniques to do so. And if there are only 50 to 100 problems, it's like, this is a glimpse in the overall landscape. And even among researchers, they even if they work on an ER complete problem, they say this problem is NP hard, and they don't cite ER completeness. And then I speak to them, I say why, and I don't know what that means. And that should change, right? We should not live in a world where we don't show what we know about something just because we are not aware of the definition that they are. So just basically this goal here is to create awareness. And do I have time for one more open problem? Yes. Yes. Uh-huh. I hope so. I should have. At least I have it in my notes somewhere. No, I think you're right. I forgot this, but I have written down this. No, I've forgotten to say this. So maybe let's answer this exam question. But given this lecture, maybe you can answer those questions. So let's maybe spend the last minute on this. So we believe NP not equal to ER. And possible reasons could be any idea? So it's like discrete versus continuous. Right. So there's this philosophical reason that NP is defined in something discrete and ETR in terms of something continuous. And we can just think, why should something that's continuous also be discrete? That would be one possible reason. Martin, you were raising your hand. You had the same idea? Something? Similar. Okay. So there's another big reason, and that's maybe the main reason, which is experience. Right. So people, there's this conference in Europe, which around 2,500 published papers every year. 2,500. Think about it. They all work, some, not all of them, but a large fraction of them work with training neural networks. No one managed to do something better than gradient descent. They improve gradient descent, and they do it in a great way, but they never managed to discretize training neural networks. So just experience. And there is another reason to believe in it, and it's a little bit like why it makes sense to believe in Christianity, right? Well, it reflects the state of the art. So even if it's not correct, in 100 years someone says, oh, but I have this extremely sophisticated algorithm, and of course we can solve ER complete problems really fast. At the moment we cannot. So everything about complexity classes may become irrelevant in 100 years, but at the moment it's not. At the moment it tells us something. So even if you, so that's why you can just assume it's not the same, because in reality we cannot solve ER complete problems in the same way we can solve NP complete problems. Is this satisfactory to you? Are you convinced by these reasons? Okay. Then yeah, let me maybe just mention that maybe a third direction. So this year is more of a fundamental problem that ER can give us, kind of give us insight into other problems. This year just is about awareness, that we see, okay, this is a phenomenon that actually appears in lots of different domains. And the third one is maybe we can find common methods, right? So this is what we do in algorithms research. We look at one problem, we find methods to solve it, and then these methods we use for another problem. And maybe we can see how these different methods translate to different domains in a mathematically rigorous way. Okay, so this was the last content lecture. On Wednesday, I will answer all your questions about the exam that you may have. Please also, if you found things in the exam, unbalanced, or there's maybe I didn't add up the points to the correct number, please send me an email and I will update the exam. And of course, Gabriella will also review it, and hopefully all errors will be eliminated.